Alrighty, so I'm creating a new series where I'm going to explain how to dissect AdventureWorks into the master data management model that I've constructed. But at the same time, I have to improve the model. So I'm going to start doing some live streams where you can actually see the work that's being done and the thought process going on. So I'm going to try to speak aloud, but then I will basically go over the code and put them in their appropriate areas. So instead of trying to redo videos multiple times, it kind of takes on the same concepts of this model where we want one to do something once and then reuse that. And in this case, it's kind of like content where I'm going to do all this work and then basically in one video series, the actual construction of the master data management model, I'll be able to say, all right, here's how I put flat together. Here's how I put something else together. And in this AdventureWorks series, I'll be able to say, all right, here's how I used those modules to import this data. So basically, let's see. The model that I've constructed is very patternistic. I have a base domain and a lot of additional attributes. I have realm, class, family types, and they all look the same in terms of columns. And I am looking to take my vertical data and create a data-driven report builder. So I'll be able to enter in data into a table and a new report is created. And it's not just report, it's maybe a select statement. You know, it's really kitty. It's really like a data set builder. So I can say, you know, maybe I have a specific select query that I use in dynamic generation SQL or dynamically generated SQL, then I can define it via data and reuse that in a larger piece module where, you know, hey, this overall query has several sub-queries and here are the order and put it together, so I'll be able to keep generating dynamically different reports or data sets, just a view of data. So all of my main domains that I'm looking at first are, you know, vertical. So I have my people table and then I have a name where each record represents a specific type based on my unique identifier. My unique index. So same thing with people identifier, people name. If I go up here, you can see PEO. So people, name, identifier, event, you know, all of these things. Instead of being vertically stored, what I want to do is create a flat database. And that's what's going to really help us get to this dynamically generated data set retrieval, where every time a row is updated, inserted, etc., it gets immediately moved over to this flattened area. And because of the foreign keys, all of the data that this particular insert or edit is expecting will already be there. So comparing the two, we have the vertical names, and I really want them horizontally. And the basic pattern for these, flat tables are we're going to define what we need and basically repeat that and delimit that or increment a number at the end of it until we hit the end of I believe about 8,000 bytes, because we want to make sure that if every single record was filled up, that SQL actually does insert it, and SQL won't perform a DML action on a record that's greater than that page itself, which is 8096 bytes. So we're going to have to do some definitions and some creation to make sure that we don't breach that. But again, the pattern in with itself, whether this is 1 or 9999, it's still going to have a name 1. The other columns that I might want 1, type 1, all the way up to maybe 30 or 40. Really, we're going to let the database tell us, because the identifier table might have different columns than the name table that need to be moved over. And as an example, pretty easy example, where address has address text and a foreign key to a address or a geography dimension, versus flag, which really just has the flag value, whether it's 1 or no or 0, versus event that has additional dates. So being spread out and creating this dataset generator where we start wherever we need to, and we maybe join dynamically, identify an event, then we can also dynamically say, hey, there's going to be this incoming JSON. It's going to match up with what we've defined in this dataset generator. So please compare, and then we can have events filtering on where it will know which set it's supposed to filter on and look at the dates. 1 second. Come here, Katie. Oh, come here, Kitty Mouse. Yeah. Okay. Meowing at me. Yeah. So the first thing that we actually need to do is define the bytes for each of our data types that we're using and make sure that we don't breach that 8096. So this will help us in determining what our max can be. So once we create this one piece of code and let's say we run out of columns, the system will automatically recognize it, create a new table, the new views, the new whatever it needs to. So it's ready to continue, and we don't have to sit there and say, oh crap, we're running low, let's manually go in here and do something. We're going to let this system build itself as it expands. So that will help us, do other things rather than be stuck in maintenance or hire more people to maintain things. Huh, kitty. So, because of all of the procedures that I created in my master data management building series, I know that when I create a new user-defined type, which will be this, how I create it is every existing database gets those user-defined types. So I know that they exist in every database, so I can really just start with one database to figure out what I'm going to need. And I'm going to be creating definitions in our system database to link them to the actual data point types. Because if I go, it would be interface. And don't mind this. These functions are explained in the system. These are my data point types, also known as the data type to a particular data point, the data point being a column in a file or a table or what have a view. So I do have them separated into flags, integers, etc., but I have that data point type name, which is going to match the actual user-defined type, the actual domain. So all I need to do first is basically create a definition for the unique number of bytes that I will run into, and then link the data point types to the bytes via our relationship structure that we use a lot. I should have a tree for that also. Come on. Yep. So in another few videos, I linked definitions to specific data point types or data sets, so we knew what columns belonged in a specific trigger or a view. So my definition itself, let's see if I have, here I could use this. the fluidity of the system. Should be able to paste this. Replace this data set with definition. And let's just use this for now. Yep, there we go. Oh. And I'll highlight the full amount so you can see the tree itself is pretty small, but once we start hitting the actual definition table, not just the realm, class, family, type, we have the specific object creators for views and what view to create, defaults, whether they should be null, true, or false. And these are linked to data point types in our system database via the relationship. So that's a good question. Do I have that here? Can I do this? Yep. It's a good part about letting the system build your objects. Like, I'm not sure if this actually got built yet, but since I said, hey, build them all around class, family, type across the board. So we have definition to procedures, to data set types, and to data points, and what they actually need to do. So that's how we're getting from a specific definition to a particular domain or user-defined type. It's basically going to say, and I can show some examples, this cleaning flag through the relationship table is probably linked to a default of, since it's not null, probably a default of false, because I said, hey, none of the new data in my system can be cleaned. You have to determine that it'll be cleaned at a later point. It's like every new piece of record in my system can't have security because you have to exist before you can have security. It's just some simple pieces of logic. So we're going to define, again, linking the data point types that we have, aka domains, to particular bytes, which will then help us create or maximize the number of columns that we can have instead of just guessing, because the name, the flat name 001 through whatever might have 40 increments, while the text, which has an varchar 2000, 1000, etc., might be smaller. So let's see. I guess where I would have to begin is just getting the bits for these. So we have about 16 combinations. I will copy this. Well, actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I have some shortcuts that I use, so I'm going to replace tab with, let's see, end quote, if data type equals this, and the other column, character maximum length, equals this. That will be numeric most of the time. Oh, I just want to do selection. There we go. Same thing with the selection. I will do At the very beginning, I want data type equals single quote. And at the very end, actually that will be fine because I already have my then. So really, the last piece is going in here and saying, well, null is a bit different. So when we have this, we actually mean is null. So now I can use Shift Alt, copy this stuff, and actually replace this. Let's see, are all these good? Yep, no nulls here. So now I'm looking for each of my unique items, and I can plug in the bytes. I know by heart, begin is 8, believe bit is 2, and varchar max. SQL's very lenient when it comes to max, so it won't count that against us. 2000 is 4 plus 2. That's 2002. That's 1002. That is 502, 202, oh, 102, 42. So I believe it's nvarchar is 2 times the number of bytes plus 2 for the actual what data type it is. I think unique identifier is 16. I will check that out. And I believe, so that's 2000. I believe for binary is 2 times the character length, and then date time. Decimal's a little weird. Date time decimal. All right. So let's go figure them out. So right on bit. So it gets more condensed the higher they are. So I was wrong on bit. Oof. Date. Three. Date time. Is it probably 16 or 8? So let's do the max. So we don't have to vary. We could just say 8 is that max. So I was wrong here, and this will, even though it will condense the more flags we have, it's fine. We'd rather be under than on the line. Date time 2, we said 8, and this was 3. So we're going to look for the max on decimal, double check unique identifier for binary, and just make sure that the nvarchar that we thought of worked. Oh, wait. 2 times plus 2, okay. Nope. Actual length plus 2, not multiplied. And what was the last one? Decimal. So we're going to do 17 on the max. I believe I use 2010. So I could do 9, but we're going to call it 17 just to be on the safe side. We don't know if, we define different decimals, different precisions. So our decimal will be 17. Our binary is actually length plus 2, and unique identifier was the last one. Byte. Sweet. Sweet. Actually, I should pull up YouTube to see if anyone's commenting. There we go. All right, so for creating the definitions, I'm going to go ahead and have other data here. I'm just going to comment out all this crap. Oop. All right. So what kind of definition do we want to classify this as? Let's see what we have. System functionality. Okay, that makes sense. Object. It's not really an object. It's really more of another word for definition. Because I hate naming things. So hard sometimes. To have a definition type inside of the definition structure seems a little redundant. We're defining something very specific as applied to rules. Okay, rules make sense. So we have system rules, and that is a new ID of 2. Yeah, this is a common rule. And what are we going to, we're going to say this is byte length. This will be 2, so byte length. Now I can close all these other tables. Come down here. This is my definition tree. System rule, common, byte length. That's excellent. So DB interface main dot DBO. System rule, common, byte length. Sweet, that comes out. It doesn't look like we have a unique value, but because we want to use the same data set, there's no real need to go further, comment out things. I'm just going to use my favorite thing, create a definition cursor. That tool I got from DevArt called SQL Complete, which will allow me to store snippets, save stuff. Makes for faster everything, really. Blatant promotion, but good stuff. We're going to call this the actual byte length. We're going to call this the definition type ID. So we need a 1, 2, 3. So data type, max length, byte length, and definition type ID. It's good to do everything in the same kind of order, so you can easily use column select to, that's the Windows key. All right. Sweet. So for each of these, definition ID, actually I'm going to switch this around. We're going to use what we're supposed to be using, and then just call data main, which is our primary data storage here. That makes more sense. So I could just kind of migrate this code over to my interface main and reuse it whenever, attach it to like the data point type creator to make sure that we're adding new definitions every time this happens. So the definition key name is going to equal byte length. And definition type ID is going to equal, and definition type ID will equal the type ID coming in. Just say if the definition ID is null, then we're going to want to insert it as our versioning data. We want to create a record for the definition table. Those are the values we are going to need. Once again, that thing was DevArt SQL complete. So let's replace null with nothing, so we can get some formatting done, and then go in and say we own this. Our tenant is going to be 1. This is actually being created by the system. This was going to be our byte length, so we can easily look it up and compare it. Description, just give it data point type byte lengths. No abbreviations. Actually, key name is going to be that, and we will create definition name equals something space the at byte length. That should look a little more readable. This will be our comparison. Sequence won't matter. It is active, it is trusted. And definition ID will be our output. So what should we say? Data point type, data point byte length of 8. All right, so definition ID and definition name. Since we are calling this inside the cursor, let's kill it. Dang it. Sweet, that should be good. Yep. Let's see, we have that query up still. Yep. Let's go ahead. Yep. We got our new byte lengths in there. So now what we're gonna have to do is, like I said, use that same procedure. I'm actually gonna save this code. Guess I'm gonna create another one that's going to link up to what we just did, and basically we need the same everything. Then we're going to change out the insert statement, or the insert execution. So what we will need is to find table value function, get system relationship tree, no defined. Actually, I think I can do definition to data point type. Sweet. Functional direct member. System. Basically what this is for is we're going to now relate the definition that we have. So we know that because we already went through and created these new definitions, that every time we execute this, we'll actually get a definition ID. So now this will be, if the definition is not null, so we actually have one, then we're going to create the relationship between the definition and the data point type. So instead of data type, we're going to need to add the actual domain back, the domain name, because the domain name is going to find what data point type it is. So that means we need a data point type. And that data point type ID is going to be changed within the cursor itself. So let's actually do it here. Select add data point type ID equals data point type ID from the table value function get data point tree. We don't care if it's a flag or anything, what its classifications are, but what we real care about is the domain name that we're going to get from this query. Domain name. And actually, because, well, this still matters. The byte length will still matter. This won't really matter anymore. We didn't do anything with that. Definition type ID will matter because we're going to look up the type ID of the byte length compared to the byte length that we've created and attach it to the domain name itself, which will be our data point type key name. Sweet. Domain name and byte length is what we need now. Okay. See if we're getting our data point types, and once again, because we're doing this inside of a cursor, we want to make sure that we clear it out so we're not, we didn't find anything. So then we're going to give this data point type from the previous iteration to some random thing that we don't know about. And we got our data point types. Select. Actually, I would already have the definition ID. So now versioning data create system relationship. Come on. Yep. Get rid of the isnal, get some formatting. Sweet. This is going to be active. We're going to trust this. We will need the system relationship ID on the output. Display order and sequence doesn't matter. We're going to need to get both of these implied numbers once. So the primary key implied child, since it's definition to data point type, the child will be the data point type, and the parent will be the definition, the type ID, and we own this. So we just need the specific data set numbers. So let's see. Do I have anything? Yep. Sweet. One for definition, one for data point type. Dang it. Sweet. Oh, and the system relationship ID. That's the last thing we need. Get our parent specific data set number implied will be for the definition, and our child will be for the data point. And that should be it. Nope. Oh. Excellent. Even though I declared it, I'm actually just selecting it and not filling my variable. There we go. Let's just see. Easier to look at it this way and try instead of trying to figure out a lot of other things. What the last items were, which was today. Type of one is correct. These look appropriate. We're getting the same definitions for different data point types, which is perfect. Excellent. So now what we've done so far, like I said, the max length of data in a particular record is 8096. Same. Come on. We have just given our original data points, columns, etc., numeric values, so we can guess how many, I mean, not really guess, but be more specific on how many sets we have. So one of the things I was working on, I might not have anymore. Oh, there we go. These data point types belong to our shared attributes. Because like I was saying, a lot of our tables are the same except for when we hit the shared attribute, which are, something event, something hashed, where we do have a realm class family type for hashed, identifier, measure, or what have you. But that type links to multiple tables. And each of those intersections, we have the original people ID. This is an extension of a person, followed by some really unique columns based on the shared attribute that we are dealing with. So sometimes measure has 4 columns, identifier has 1. Let me do this a little bit. Address has 2, text has 4, name has 1. What's going to happen is in our flattened piece, the other columns are actually going to be those additional 4, 2, 1. So based on what we're looking at, this would have 1 here, this would have 1 here, but a measure might have a group of 4 columns repeated over and over and over again. So now that we have the data points, I could say, data point type ID, just to get an example of where we're at here and the work that we've done. This is a simple query, and I will actually block all this out. Sweet. So I'm going to need to create another relationship to relate these as very specific things that I want, because we'll run into tables that we're not going to flatten at all. These are very specific data set types that represent the measures. So in these measures, if let's say left join the relationship table on relationship I think it's primary key. Yep. So definition to data set, or definition to data point type. Here's the data point. Data point has a data point type inside of it. So I could say the child and this relationship, the type ID is going to equal definition to data point type, the functional relationship, it's a direct member of, So this is going to expand a lot because of all the definitions that we have. It's not going to really make any sense because we have to close the relationship. So we are any definition to data type. So whether it's a view or a trigger, a default, plus the data we just entered in. So I'm going to actually condense this down and say interjoin the definition. Actually, I could still do left. Ref definition. On the system relationships, parent implied equals the definition ID. And I'm going to filter this down. The definition type that we just recently added was, it was a system definition, and it was a rule, a common one at that, for byte length. Oh. And we own it. So now it condensed down, so we should be able to get the definition key name. And this is telling us how many bytes are in a particular set. Let's get an order in here so we can order by dataset name. So at first glance, date was 3 bytes like we had defined. We said we're going to use the max on date time, even though it was 6, 7, and 8. We said, okay, we're going to use 8. A big int we know is 8. So this must be, varbin data. It's going to be varbin 2000. So that's 2002 bytes. And here's our text at the higher end. Boom. So now we want to go in and kind of look at creating yet another definition, because we don't want to look up and sum this. We don't want to say, okay, not just these types. So we're looking at particular data set types. Do we have data point types? Nope, because these are just the additional ones. What we want to do is we want to say what other things about the original record do we want to look at, if it exists. So assuredly, creating our list, we're going to call this set of stuff additional columns. Because if you followed the series, which I'll have a link in the description for video 1, if you followed the series, you'll understand that aside from the names, the columns are basically the same for 97, 98% of the tables that we create, especially in the realm class family type. The class has a taxonomy ID. The family has a taxonomy ID, which points up to the class. The class has a taxonomy ID, which points up. So we have all of these very specific things, these very specific patterns. All of these have other flags and active flags and that sort sequences. So now we have to kind of figure out, when we're flattening this, we're going to be creating this massive data set creator, report generator, what have you, given a snapshot of time. So what really matters in doing this? Are we really going to take all of this stuff? Are we going to take the description? Does the description really matter in a report per se? Or is it just, it's just a description of the record where most of them might be null, some might exist, or they might be defined as well as the versioning or as the names and the key names themselves. So the additional columns that we look at per group is, we know in the header record of something, we have a tenant. We have an owner of this record. So who owns this particular piece of data? It's not a one, it's not the system. So because it's not the system, or just because of the tenant in general, we know that because this is the header record, all of these will already have the same. Actually, that would be in there. Oh, those are recipes. So we have text. Not yet. What do I know exists? Ingredients. I know ingredients exist. Or food. The food would be owned by a particular group or application. So in there, damn it. So I'm working on this application with my wife. So we have ingredient. What's our measure? There we go. I don't know what's been filled out yet. So we have a header record of like ingredients. We have our specific ingredients, whether 14 ounces, 1 cup of water. But because that's a header record, we know whoever owns it is going to own what's attached to it, because that's just the nature of the system. So we could guess and safely assume that it's already owned by the tenant. So we only need one spot for a tenant in our generation. Let me close all this down. I'm going to save this too. Here we go. So we don't have to say that we want the tenant for these additional extensions of the original table, the shared attribute intersections. But we do want the type ID or the taxonomy ID, because we want to know if we hit, like I have a bot in here and we have posts for a ton of different things. So I have a bot that scrapes Reddit. We have descriptions for the recipes. So now I know when we get to the text that we're going to have different types of text, whether they're headings or actual or titles or actual posts inside. And these are all split out for indexing to condense how we're storing things. But the types vary. So we're going to want to know what kind of type of information it is when it comes out of the system. So the taxonomy will help us fill this out. So we'll have these additional columns that are defined. The taxonomy. So additional columns, the taxonomy, and kind of like what else do we want? Do I want the description? No, I don't care about it. Do I want an abbreviation? Actually, yes. Abbreviation and the column header might be important when generating reports. Some sort of abbreviation, and the column header is for pivoting, because we'll be able to dynamically create something that pivots it. The key name I definitely want, and the name itself. The active flag, because we're going to, again, like I said, all of our tables are in some sort of pattern. They look the same. So when we build these long tables, this is not just the information you'll see. You'll see if it's not the header of these flattened tables, you'll still get your information that you need. The type ID will no longer be relevant for these flattened tables because they're flattened. The type ID exists in multiple places. So what we'll have is the tenant per record. And then we'll have, underscore 1 through, we don't know yet. That's why we have this stuff right here. And then we'll have our active and security and plan flags and everything to let us know, do we have access to it. We're not going to have the cleanse to and cleaning. It doesn't really matter in the flattened version, but then the flattened version will be bounced again to a warehouse version where instead of cleaning, we'll have basically the previous ID. So we can make a change, basically. The delta between the two, this record, the record before, and we can keep going back as far as we need, just in a flat or in a vertical or horizontal data set. So name, abbreviation, column header, I definitely want. Key name, I definitely want. Sequence, I want. Display order doesn't really mean anything anymore. The display order is for the application side. So it's really, what are you ordering on? Actually, no. Most of those are going to be null anyways. So that'll be it. We'll have our additional columns, 1, 2, 3, 4, 5, 6, 7, plus our 7 main columns. And these are not going to be for, these are only going to be for our extended tables. For our base table, it's almost the same as the original record. There's some other parts in the system that haven't been created yet that we'll do because the other database stores additional notes, development notes, and GUIDs and stuff like that. And for the realm class family types, what we're going to do is we're going to have one table. That was something I was working on up here. We're going to have one table that has them all in one location. And that primary key, because the order of operations that you must do in order to get data into the system, you can't put something in a base type table without a type ID, a taxonomy ID. You can't put anything in the type table without a family, anything in the without a class, etc. So when the trigger or the process fires to on a realm creation, this will get created while this data is null, and then the class will get created. So this will get created under that class, and it'll keep going down until you have that full item. And then when we come back into the header records or the base tables of, decisions, one of them, or the actual shared attribute, the domain tables, all the type information will exist. So the trigger will go find the class family type that's associated with it and give it a new ID, a new single ID. So our type here won't actually be the original type. It'll be a brand new type from this giant tree of all of our taxonomies. And what this will allow us to do in the dataset generation is assign this column to another particular type as we're generating that says send this value to a function. And that function will be able to give us the specific taxonomy that we need. So we'll have a function to get the realm key name from an ID, the realm class family type for functions to get each particular part from that new primary key type ID that we're going to be creating in this giant tree. You again? Come here. Come here. So actually, I think we can create that one first. So let's go to the flat database and make sure that I have everything that I need. Is this the reference? Sweet. So I am going to I'll just take a random one. Let's do the class. I'm going to create. Actually, I only need the create itself because we'll get our, we already have patterns built in the system that's going to choose the default indexes and the actual defaults and all that stuff. So we're going to have a taxonomy tree. Start replacing stuff. So first, data main is now going to be flat main. Equipment class, the table that I pulled from, is actually going to be a taxonomy tree. It needs its own specific dataset number. And would we get use out of any of this? I do not believe so. Will we get use for cleaning? That's a good question. Well, we have heuristics. Actually, I think so. I think we'll get use out of a cleaning, but through a different area. I think that we will get better use out of a cleaning here. Oh, kitty. And this is, so in my system, let's say if I type in the wrong country, Oregon, GUN, right? But I already have a state list and I have Oregon in the state list already. I can look at GUN and say, hey, I want you to clean this to the appropriate state. And all of the new data coming in will get rerouted before it's saved. So we're basically cleaning on the fly, or depending on what your business is, what you want to do. You don't have to clean it coming in. You can clean it in the report, during a process, or never at all, and just create a relationship between what we know is the real value and what they've entered to preserve the integrity of this is what it actually is, but for some reason you called it this. And by adding that cleaning to the different realms, classes, family types, what we have is the ability to say, hey, when you're pulling this data, it might actually be cleaned because maybe the type was updated to be cleaned, but all of the bad data wasn't updated yet. So during the period of time between the type being toggled to start cleaning to a different type and when the actual underlying data is resolved to the new type, our system will still work and adjust itself accordingly instead of, having this, well, we're going through a cleaning process, reports are down for who knows how, when, or how long. So the idea of, my idea of putting these cleaning flags in here, let me fix this before I get, will help us determine at what point in time are we in that process versus this is being cleaned now, so clean it on the report, don't clean it on the report, or to allow it to adjust itself when it does get resolved. A report might be different depending on when you have ran it based on what your cleaning thing is. So having a tree like this, yep. So essentially we're going to be table value function get, doesn't matter. I actually don't have anything in there. Measure. There we go. One, no. What else do we have? Name, I guess. We got some names. So we're going to be creating this giant list of multiple trees, all of the data that we have, so we can look at it with additional columns, because these tree functions are specifically used in the main system and what our flat database is for some sort of reporting, some sort of generation that is outside of the actual main application itself. And it's kind of really hard to, there's some gray area and then clear black and whites. Like, are you going to be pulling from the flat database your country drop-down menu? No, not at all. Not at all. That's what these hypernormalized tables are for, the modular pieces to create components for your application and to ingest the data in, whereas the reporting is more for the aggregation side and the analysis side of, well, what is actually happening, what do we have, and what is happening. So that is kind of what the flat database is for. Although we can reuse it in some aspects for this live look at what is going on. So like importing AdventureWorks into this system, what I'll want to do is, if I import person, I'm going to import all of this data into a real data model of vertical storage. And as it's being imported, it's actually going to get moved to the flat area. And what that'll allow me to do is to create a report to essentially check to see if whatever I imported matches the original table. So it'll give me a nice little data-driven testing capability, like hands-free, where I say, hey, here are the columns in this specific table and database. I fill out the mapping, all data-driven. This column goes to this RCFT or is this particular type ID, however we want to do it. And once I create those mappings, hey, this goes here, it's not SQL anymore, it's all data. Then I basically hit a button, it says, okay, looks at people identifier for the primary key, and the people identifier says, hey, this is a business entity. So this will be my comparison to the new person ID. Do I have a person ID under this business entity? If yes, then maybe I update or maybe I skip. If no, all right, start sending these to the people name. Each of these have a different type, so they'll be vertical, etc. All module, all data driven. And at the very end, we want to, generate the report, hopefully using the same type of technology, and then compare the report data set to the input data set to make sure that they match. Because if we can create the original data set post splitting apart and moving to flat, then we know that it was completely successful. If we're missing records or if they don't match up, we know that something went wrong and we can reverse the process. So that's really hands-free. Why are we doing all this work? It's a very common pattern, so let's do it this way. Actually close this. So going to the table creation, I think this is going to be fine for now. I was trying to get ahead of myself here. Oh. Actually, let's just get rid of a lot of stuff. Actually, how does SQL does it at the end? Okay. So our tree won't have a taxonomy ID for now. It'll have the flags that all of our tables use, a tree, an owner, and a specific table identifier that lets us know that, hey, this is the specific table that we're looking at, which we're going to be using a lot. And then we'll have our data points. Actually, I should just this is going to be a pattern. There we go. When you think about the difference between these, because in our vertical storage, we have keys linking them, But in this flattened storage, we might get a realm without any classes or families or anything like that. So we have to make sure that they basically update, because what's going to happen is no matter what, once we have the type change, and actually, should we do it like that? Should we have a spot for a blank realm that eventually gets filled in? Or I think this is a little better if we base it off the type only, since everything has a type. Let's see, family. Yep. So whenever a type changes, it's going to make sure that the entire record is here. So I think that's how I'll approach this problem. Instead of saying, okay, when a realm changes, if you don't find the realm with nothing under it, then create a record. And if family changes, where there's a realm matching that, or class changes, but there's a realm matching it, update that record, etc., etc. Because then if you enter in another class, this record will basically duplicate another class under the same realm, if that makes any sense whatsoever. But actually, if I go on the type, then I have a lot less firing going on. Only when types change will I get the entire tree filled out. And I will only have to basically look at the type primary key and the specific data set number to say, hey, this is a text type, or this is a measure type, or a flag type. That's where I'll be matching on to make sure everything else is updated. So I think that will be a better approach. Instead of firing on every single realm, class, family edit, and type edit, I'll just focus on the type edit for this particular tree. Cross fingers. Oh, equipment. Sweet. Wonder how long I've been at this. I'm gonna take a short break, probably come back today. Created our relationships so far. No, thank you. To define the byte length of the data types that we're going to be using to make sure that all of these are filled out in a vertical format. But in order to get that, in order to create these tables, we first must take all of our realm, class, family type trees and convert them down to a more consistent ID, like a surrogate or ID for new types, so we can easily pull whatever piece we need and have this extremely large ability to filter on various levels. So that's what we got so far: linking definition to dataset type and bringing building our first flat table. And like I said, thanks for tuning in. What I will be doing is taking a quick break. I'll come back and start adding triggers to fill in this type table. So just get on with it. I need something to eat. I'm getting all messed up. Getting tired. But I'll be back very soon. Thanks again for watching, and I don't know, 30 minutes? I'll see you then.